For many years, researchers thought the cosmos was immense, yet ultimately quantifiable, spanning roughly 14 billion light-years in all directions and holding several hundred billion galaxies. The James Webb Space Telescope swiftly altered this perspective, unveiling an observable cosmos that stretched 93 billion light-years wide and teemed with galaxies. Within what previously appeared to be void darkness, Webb discovered fully developed galaxies merely 300 million years post-Big Bang, alongside black holes expanding at incredible rates. Additionally, it found structures disproportionately massive for their age. However, the most disturbing revelation isn't just the extent of Webb's vision, but rather what these observations imply. This concerns what exists beyond our cosmic boundary, and why a significant portion of the universe might remain perpetually inaccessible. If you're prepared, please press the like button and subscribe. Let's collectively explore the latest discoveries made by James Webb. To grasp the true insights the James Webb Space Telescope is providing, we must first discard the notion that space is merely something we observe across. In the cosmos, distance and time are intrinsically linked. Each ray of light bears its own history. This includes a temporal marker indicating when its voyage commenced. Light travels at a consistent velocity, approximately 186,000 miles per second, which is rapid enough to circumnavigate Earth, over 7 times within 1 second. Nevertheless, even at such a pace, distance instantly translates into a time lag. When you view an object a mile distant, you perceive it as it appeared a few millionths of a second earlier. Observing the moon shows it as it was 8 seconds ago. The sun visible in the sky is not in its current position, but rather where it stood 8 minutes prior. These temporal lags are sufficiently minor that they seldom register with us, yet as our observation extends further, this phenomenon intensifies, ultimately altering our comprehension of the universe itself. The closest star apart from our sun is seen by us as it existed over 4 years in the past. The core of the Milky Way appears as it was 26,000 years ago. Furthermore, when we gaze past our own galaxy into the immense void separating galaxies, we are no longer witnessing the universe in its present state. Instead, we are perusing earlier segments of a narrative that is already billions of years old. Consequently, the night sky is not a mere snapshot. It functions as an archive. The James Webb Telescope was engineered precisely to decipher the most ancient, dimmest pages within that archive. It achieves this not by seeking out more luminous entities, but rather by detecting light that has undergone alteration due to the universe's own expansion. As the cosmos expands, space itself extends, and when space extends, it elongates the light traversing through it. Wavelengths become extended, causing energetic blue and ultraviolet light to transition into red and ultimately into infrared. This phenomenon, termed redshift, functions as a celestial chronometer. The greater the stretching of the light, the longer its journey has been. And this also indicates an earlier emission point in the universe's timeline. Prior telescopes, such as Hubble, were primarily optimized, chiefly for visible and ultraviolet light, the limited portion of the spectrum that human eyes developed to perceive. This optimization rendered them exceptionally potent instruments. While useful for examining proximate galaxies and star-birth regions, the deeper into the past astronomers attempted to peer, the more the cosmos eluded their sight. Primeval galaxies hadn't disappeared. Their emissions merely traveled beyond the range of prior instruments. The James Webb Space Telescope was constructed to reveal what had previously been unseen. Its primary mirror, exceeding 21 feet in diameter and covered with a minuscule gold film, possesses exceptional sensitivity to infrared light. Instead of circling our planet, Webb functions almost 1 million miles distant, positioned at a gravitationally stable point, allowing it to stay exceptionally frigid and protected from thermal and optical interference. Within that profound cold, Webb is capable of discerning photons so dim that their journey across the universe has spanned over 13 billion years. As Webb gazes into areas, what appear as utterly dark regions to human vision are not being searched for void. Rather, it anticipates light that has been elongated nearly to the point of imperceptibility due to cosmic expansion. And what it uncovers there is not a serene, nascent cosmos merely starting to take shape. Instead, it reveals a universe already bustling with activity. Some of the galaxies Webb has identified, these came into existence when the cosmos was merely approximately 300 million years old, constituting less than 3% of its present duration. To comprehend the extreme earliness of this period, envision condensing the complete chronology of the universe into a solitary year. These galaxies would emerge on the second day of January. In accordance with established models, this epoch, referred to as the cosmic dawn, was predicted to be comparatively faint. The initial stars were anticipated to ignite gradually, coalescing into modest, delicate galaxies that would require hundreds of millions of years to evolve into anything significant, sizable, and luminous. Highly structured galaxies were presumed to appear considerably later. However, Webb observed galaxies that were already colossal, actively generating stars at prodigious rates, and already configured in manners that ought not to have been feasible so early. Several of them possess sufficient luminosity that even if situated 10 times more distantly, Webb would still be able to discern them. Such brilliance entails repercussions. Luminous galaxies necessitate vast quantities of stars, and these stars generate heavy elements, such as carbon and oxygen, which exclusively originate within stellar nuclei and are dispersed upon a star's demise. Observing these elements at such an early stage indicates that prior stellar generations must have already emerged, completed their life cycles, and disseminated their constituent matter throughout the cosmos. Put differently, the universe did not gradually transition into complexity. Rather, it rapidly progressed towards it. Furthermore, there is an element of profound humility regarding the endurance necessary to observe this primeval light. To image some of these galaxies, Webb fixates on a solitary celestial region for numerous hours, occasionally even days, accumulating individual photons. Each of these photons has traversed almost the entirety of the discernible universe, enduring cosmic expansion, attenuation, and immeasurable distances, merely to conclude its voyage on a sensor smaller than a coin. When that light commenced its journey, Earth was non-existent, and the sun had not yet coalesced. The Milky Way was still in the process of assembling itself from gas and dark matter clouds. Dinosaurs, oceans, civilizations were all yet to come. Everything transpired while those photons were already traveling. By the moment we observe them, we are not seeing current events. Instead, we are observing an event that occurred far in the past and will not recur in precisely the same manner. This is the reason astronomers state, the James Webb Space Telescope doesn't merely peer into the distant cosmos, it gazes into the past. Spatial separation transforms into a chronological sequence with closer celestial bodies, displaying the universe in its present state, while remote ones unveil progressively earlier phases of cosmic evolution. Nevertheless, even the Webb telescope's remarkable observational capability possesses an inherent constraint. No instrument, regardless of its strength, can perceive beyond a limit established by the laws of physics. This demarcation is determined by the maximum distance light has traversed since the cosmos originated. This region is known as the observable universe, an immense spherical volume with Earth at its core, possessing a radius of approximately 46.5 billion light-years. The James Webb Space Telescope is currently extending observations nearer to this limit than previously possible, identifying galaxies at ranges formerly considered inaccessible. However, even Webb is unable to view past the cosmic horizon, and here the understanding becomes disquieting. Space does not conclude at the periphery of our observational capacity. Past that boundary, galaxies continue to exist, stars still form and expire, black holes still coalesce, and complete cosmic narratives develop in areas permanently concealed from our view. No transmissions from those locations can ever arrive at Earth, not due to insufficient technology, but because space itself is undergoing excessively rapid expansion. The James Webb Space Telescope has not only demonstrated the extent of our visual reach, but has also revealed how much of the cosmos remains perpetually out of sight. And as we assimilate the discoveries Webb has unveiled within our perceptible cosmic region, the immense quantity of galaxies, the rapid pace of structural formation, along with the surprising luminosity of the nascent universe, a more profound inquiry starts to surface. If such an abundance exists within the tiny portion of the cosmos visible to us, what implications does that hold for the actual magnitude of all that lies beyond our perception? For the majority of contemporary astronomy, the nascent universe was conceptualized as a gradual and delicate environment. Following the Big Bang, space expanded, temperatures decreased, and matter dispersed nearly uniformly throughout the cosmos. Minute variations were present, areas that possessed marginally greater density than others. However, gravity was anticipated to operate slowly over hundreds of millions of years. Gas would cool, coalesce, and ultimately ignite the initial stars. Galaxies, according to this model, would progressively appear initially small and dim, expanding in size, solely after extended durations of calm accretion. When the Webb telescope commenced its examination of the early universe, astronomers anticipated discovering merely a few rudimentary galaxies within the initial few hundred million years following the Big Bang. Instead, Webb uncovered multitudes. Luminous galaxies were observed repeatedly. During periods expected to be largely devoid, these weren't faint, loosely connected sparks. Rather, they were already bustling hubs of stellar creation. The issue wasn't merely a single unusual finding by Webb. Instead, it uncovered an excessive number. Within the initial 500 million years of the cosmos, Webb observed galaxies emitting vast quantities of light. Certain ones encompassed material equivalent to hundreds of millions or even billions of stellar masses. Such a quantity of mass ought to have necessitated considerably more time for its accumulation than the universe's age permitted. While gravity possesses immense strength, its action is not rapid. Gas needs to shed energy prior to its collapse, and dark matter halos must attain sufficient size to ensnare conventional matter. Stars need millions of years to develop, and subsequently, these stars must complete their life cycles to infuse the ambient gas with denser elements. Every stage dictates a minimum duration. Excessive compression of this process violates physical laws. Nevertheless, the galaxies existed. Among the most disquieting revelations was the extent to which these nascent galaxies seemed chemically advanced. Webb's spectroscopic analyses unveiled not only hydrogen and helium, the elements created soon after the Big Bang, but also carbon, oxygen, and nitrogen. These particular elements are synthesized within stars and are only dispersed upon a star's demise. Their existence implied that a minimum of a preceding generation of stars must have already emerged and concluded its existence, all occurring within the initial few hundred million years of the cosmos. The universe's timeline was effectively being rewound. To grasp the profound implications of this finding, it is helpful to conceptualize galaxy formation as analogous to constructing a metropolis. One cannot erect skyscrapers prior to the establishment of roads, nor can concrete be poured before steel has been fabricated. Every stage is contingent upon its predecessor. The nascent universe was presumed to be in the foundational stages. Instead, Webb discovered completed structures. This inconsistency came to be recognized as the too much light, too early conundrum. Upon astronomers' computations of the total luminosity galaxies were anticipated to generate during the universe's initial billion years, the theoretical forecasts proved insufficient. Webb's observed data surpassed those projections by multipliers of 2, 5, and occasionally even 10. A disparity of this magnitude does not constitute a mere rounding error. It indicates that a fundamental component is absent from the current model. Researchers meticulously examined every apparent explanation, including verifying the instrumentation. They subjected the data to reanalysis. They investigated whether phenomena such as dust, gravitational lensing, or inherent observational bias might be causing galaxies to seem more luminous than their actual state. Yet, repeatedly, the figures remained consistent. The universe's nascent period was not faint, it was brilliantly luminous. Certain of these primordial galaxies possess such immense mass that astronomers, for a time, designated them as universe breakers. Their presence appeared to contravene the constraints established by cosmology itself. In accordance with conventional models, galaxies of such proportions ought not to exist at those early epochs, unless the universe operated in a manner significantly divergent from our understanding. Initially, a number of scientists harbored the hope that the masses had been overestimated. Perhaps the emitted light did not originate solely from stars, or perhaps supermassive black holes situated at their cores were responsible. Added extra luminosity, causing galaxies to appear bigger than their true size. Later examination revealed this explanation was only a partial solution. Despite factoring in black hole activity, the nascent universe still possessed approximately double the number of massive galaxies compared to model forecasts. The discrepancy lessened, yet it persisted. This trend was observed repeatedly across numerous surveys, with Webb examining various directions using diverse tools. Examining various wavelengths consistently yielded the same outcome. The nascent cosmos was densely populated, and galaxies developed rapidly. Stellar creation occurred at exceptional speeds, compelling researchers to reevaluate the universe's efficiency in converting gas into stars in the contemporary era. The process of star formation is remarkably inefficient. The majority of galactic gas never transforms into stars, instead being heated, dispersed by stellar winds, or agitated by turbulence. A molecular cloud could require millions of years to generate just a few stars before scattering, but primordial galaxies apparently behaved in an alternative manner. A potential explanation is that the nascent universe was simply more compact, with matter compressed more closely, leading to more frequent collisions of gas clouds, initiating swift collapse. An alternative theory proposes that the initial stars originated from almost entirely hydrogen and helium. Lacking heavy elements that modify cooling characteristics, this less complex gas might have collapsed more effectively than today's metal-rich gas. Additionally, mergers played a part in the early universe. Galaxies were in closer proximity, resulting in more frequent collisions. When galaxies combine, gas is propelled towards their core, compressed to incredibly high densities, sparking intense episodes of star formation. A galaxy might accumulate a significant portion of its mass through brief, powerful events instead of gradual accretion. Individually, none of these proposed solutions completely resolve the issue. They offer assistance but fail to close the discrepancy between theoretical models and empirical findings. Within the core of numerous such galaxies lies a further enigma: black holes that expanded excessively quickly. Webb has detected supermassive black holes. Already present when the cosmos was under 500 million years old, some possess masses millions or even billions of times greater than our suns. Based on standard physics, this should be impossible. Black holes emerge from the collapse of massive stars. The ensuing black hole could weigh several dozen times the sun's mass. From that point, it can expand by absorbing nearby material, but this expansion is constrained as radiation from incoming gas exerts an opposing force, impeding the rate at which matter can accrete. Even in optimal circumstances, forming a black hole with a billion solar masses ought to require considerably more time than was available in the early universe. Nevertheless, Webb continues to discover them. This has compelled astronomers to contemplate unconventional hypotheses. Perhaps certain black holes did not originate from stars, but rather from the immediate collapse of enormous gas clouds, completely bypassing the stellar phase, or possibly from unusual primordial stars, became thousands of times larger than their present-day counterparts, directly collapsing into massive black holes. Alternatively, perhaps the merging of black holes occurred much more frequently within the dense, early cosmos than previously understood. While each concept pushes the boundaries of our current knowledge, none can be immediately disregarded. What renders this era particularly significant is how these nascent galaxies and black holes influenced all subsequent developments. The emitted radiation altered the cosmos, removing electrons from hydrogen atoms, through a process known as ionization. Their supernovae enriched the void with heavier elements, and their gravitational pull drew matter together into the initial large-scale formations. If these emerged sooner, and with greater efficiency than anticipated, then the whole chronology of cosmic development changes. As Webb delves further, the emerging pattern becomes increasingly distinct. The cosmos did not leisurely evolve into complexity, rather it hastened. It constructed structures at a pace that defies our most advanced calculations, leading to a stark understanding. If the cosmos was capable of forming galaxies, stars, and black holes with such rapidity, then the magnitude of what exists now, billions of years subsequently, could be vastly greater than we had ever conceived. This understanding becomes undeniable when Webb performs an even more disquieting action. It quantifies the actual number of galaxies. Throughout the majority of the 20th century, astronomers held the conviction that they possessed a fair approximation of the total number of galaxies present in the cosmos. The approach was, in essence, uncomplicated. Direct a potent telescope towards a minuscule area of the sky, tally every visible galaxy, and then extrapolate that figure to encompass the whole observable expanse. When the Hubble Space Telescope conducted its most profound observations, it uncovered almost 10,000 galaxies, within an area no bigger than a grain of sand viewed at arm's length. From this, researchers deduced that the universe comprised approximately several hundred billion galaxies. That figure was astounding, yet it proved incorrect. When the James Webb Space Telescope re-examined those identical celestial areas, the disparity was instant and disturbing. Where Hubble perceived void between galaxies, Webb discerned subtle infrared emissions. Blurs transformed into discernible structures. What previously seemed vacant was abruptly teeming with previously unseen entities. The explanation wasn't that Hubble had overlooked them due to oversight or insufficient clarity, but rather that these galaxies were concealed in plain view, their light having been redshifted so extensively into the infrared spectrum by the universe's expansion that Hubble was simply unable to perceive them. Webb was engineered precisely to identify that particular light. During a single deep field observation, Webb examined a celestial area marginally exceeding the size of 3 full moons. Across hundreds of hours, it gathered over 10,000 distinct exposures, then combined them into one cohesive image. The outcome was astonishing. Almost 800,000 unique galaxies occupied the field of view. 800,000 galaxies in a segment of sky that most individuals would disregard as barren. To grasp the implications of this for scale, picture reproducing the renowned Hubble ultra-deep field image on a typical piece of paper. To display the Webb image with an equivalent degree of detail, the print would have to exceed 13 feet in height. Measuring 13 feet in width, a wall-sized depiction of cosmic history, where each luminous point within this artwork represents a galaxy, not a star. Every single galaxy holds millions, billions, or even trillions of stars. Numerous galaxies harbor planetary systems, and a significant number possess conditions conducive to intricate chemical processes. The universe, as it happens, is far from being sparsely populated by isolated pockets of matter floating in the void. Instead, it is densely filled, highly organized, and multi-layered, bustling with activity across all magnitudes. The heightened significance of this discovery stems from the fact that Webb didn't merely enumerate galaxies, it meticulously measured them. For every single galaxy, researchers are able to determine its distance, its mass, the rate at which stars are forming within it, and its age. This capability enables astronomers to piece together the evolutionary journey of galaxies throughout almost the entire span of cosmic history. A distinct pattern emerged from this reconstruction. Galaxies are not randomly dispersed throughout space. Rather, they congregate, assembling themselves along unseen filaments. They completely steer clear of enormous areas. At its grandest scales, the universe bears a resemblance to a cosmic web, with strands of matter extending throughout space, converging at concentrated points, or nodes, where clusters of galaxies take shape, and separated by immense empty regions where virtually nothing resides. Webb's infrared capabilities unveiled this arrangement with unparalleled distinctness. A considerable number of the galaxies it identified were obscured by cosmic dust, which obstructs visible light yet permits infrared wavelengths to penetrate. Consequently, vast groups of dusty, star-forming galaxies abruptly became visible, populating areas that previous observations had registered as empty. This is crucial because the arrangement of galaxies provides insights into the universe's expansion. The cosmic web originated from minute density variations that existed soon after the Big Bang. Areas possessing a slightly higher density than the average exerted a marginally more powerful gravitational attraction. Gradually, matter streamed into these regions, thereby intensifying these disparities. Gravity sculpted space into interconnected filaments and nodes, simultaneously creating immense, less dense voids. Consider the analogy of rainwater traversing irregular landscapes. Water collects in valleys, forming channels and rivers, while elevated areas remain arid. Eventually, the topography develops a defined structure. The universe underwent a very similar evolution, with the key difference being that the flowing material was matter itself. Webb's findings corroborate that this process was already significantly advanced, remarkably early in the universe's timeline. Filaments spanning tens of millions of light-years were already present, even when the cosmos was merely a few billion years old. Certain structures exhibited such immense size and intricate organization that they defied previous assumptions regarding the speed at which matter could self-organize. A particularly remarkable instance is a formation that astronomers have designated as the cosmic vine. This structure comprises a closely clustered chain of at least 20 galaxies, extending over 13 million light-years in length. These galaxies were present when the universe was just a few billion years old, yet this formation competes in scale with structures considerably more ancient. The cosmic vine's particular fascination lies not solely in its immense size, but also in its current condition. Several of its most massive galaxies have already ceased the process of star formation. These galaxies are considered quiescent, indicating that they have either depleted or lost the necessary gas required for generating new stars. This occurrence is atypical at such an early stage in cosmic history, a period when the majority of galaxies are still vigorously producing stars. The inference drawn is that environmental conditions are significant. Galaxies situated in dense areas develop uniquely compared to those in isolation, experiencing interactions and mergers. Moreover, the severe circumstances of congested cosmic areas can quicken a galaxy's life progression, compelling it to mature rapidly and deplete its resources early. This situation is not an isolated incident. By utilizing Webb data, astronomers put together the most extensive and thorough catalog of galaxy groups ever created, pinpointing more than 1,600 groups and protoclusters. These collections, ranging from roughly 12 billion years ago to only a few billion years ago, serve as the foundational elements for the massive galaxy clusters present in the current era. Galaxy clusters. By contrasting groups found at varying distances, scientists are able to observe the development of structure over time. Early groups exhibit a chaotic nature, where irregular galaxies are rapidly generating stars. Subsequent groups demonstrate increased organization. Galaxies become more uniform. The rate of star formation diminishes and their surroundings are increasingly controlled by gravity and heated gas. This uninterrupted observation spanning billions of years was simply unachievable before the advent of Webb. Yet, despite all this observed density and arrangement, the cosmos is equally characterized by its vast emptiness. Between the threads of the cosmic web exist immense voids, expanses covering tens to hundreds of millions of light-years, which contain only a handful of galaxies. These voids are not minor spaces. Instead, they represent the most expansive continuous formations in the universe by volume. Should you be able to position yourself at the core of one of these voids and gaze in any direction, you would perceive only darkness, stretching for tens of millions of light-years before reaching the nearest galaxy. Complete cosmic regions did not manage to collect matter simply because gravity pulled that matter to different locations. The presence of these voids emphasizes a disturbing fact. The universe failed to distribute matter uniformly. Instead, it gathered almost all material into slender filaments and compact nodes, thereby leaving behind immense cosmic deserts. Webb's deep field observations vividly display this contrast within the same image. Compact groupings of galaxies are visible next to vast, dark expanses containing almost nothing. The universe is simultaneously densely packed and utterly empty, depending on your vantage point. This brings us back to numerical considerations. If Webb's deep fields are indeed representative, and various observations in different directions suggest this is the case, Then, the overall count of galaxies within the observable universe might potentially be trillions, instead of just hundreds of billions. This adjustment fundamentally changes everything. It signifies a greater number of stars than previously conceived, more planetary systems, increased chemical diversity, and additional opportunities for complexity to arise. For every galaxy we previously believed to exist, there might be 10 more concealed beyond the capabilities of earlier telescopes. Yet, even this astonishing abundance is confined solely within the observable cosmos. Beyond that limit, space persists, galaxies endure, and structure continues. James Webb has revealed to us that even the segment of the universe visible to us is considerably more expansive and densely populated than we had previously thought, which in turn raises an even more profound question. Given the richness of reality within our visible limits, what does this imply about the vastness of all that remains unseen? Initially, the cosmos appears uncomplicated. Approximately 13.8 billion years have passed since the Big Bang. Given that light moves at a constant velocity, it seems logical to presume that the most distant objects we are able to perceive would be roughly 13.8 billion light-years distant. For an extended period, even scientific experts discuss the cosmos using this framework, yet that initial understanding proves profoundly inaccurate. The observable cosmos does not possess a radius of 13.8 billion light-years. Instead, its radius measures approximately 46.5 billion light-years, resulting in a total diameter of roughly 93 billion light-years. This figure is not a speculative estimate, rather it represents a measured outcome validated by observations of the universe's expansion. The reason this particular number appears implausible stems from the fact that it conflicts with our innate perception of movement. While it remains true that nothing can traverse space faster than light, that principle continues to be valid. However, the universe has discovered a method to circumvent this, not by violating the speed barrier, but by elongating the very path. Space is not stationary, it undergoes expansion. When we state that galaxies are receding from us, it's natural to picture them hurtling outwards like fragments from an explosion. This mental picture is incorrect. Galaxies largely remain stationary in relation to their immediate environments. What is actually altering is the expanse separating them. A helpful comparison involves a balloon adorned with dots on its exterior. As this balloon expands, the dots become more distant from one another, not due to them creeping along the surface, but because the surface itself is elongating. No single dot occupies the center. Each dot perceives all other dots receding. The universe operates in an identical fashion. When a far-off galaxy emitted the light we observe presently, it was considerably nearer to us than its current position. Throughout the billions of years that light journeyed towards Earth, the void between our location and that galaxy steadily grew. By the moment the light eventually reached us, the galaxy itself had been transported tens of billions of light-years further away. This explains our ability to detect galaxies whose emitted light has been en route for 13.5 billion years, even though their present separation exceeds 46 billion light-years. In essence, light has been traversing a path akin to a treadmill. At times, it made headway. At other times, the expansion drew its target further off. The crucial point is that during the early stages of the universe's existence, expansion proceeded at a slower pace, enabling light to advance. Subsequently, expansion quickened, elongating distances more rapidly than light could traverse them. This phenomenon establishes a limit referred to as the cosmic horizon, which is not a tangible boundary. There exists no barrier or demarcation point where the cosmos ceases. Rather, it signifies the extent of what we are capable of perceiving. Beyond that particular horizon, light has not had, nor will it ever have, sufficient time to arrive at our location. It is at this juncture that the universe takes on a profoundly peculiar character. Spatial areas extend beyond 46.5 billion light-years, a fact we deduce from the cosmos's seemingly smooth and consistent appearance. In every direction one gazes, no indication of a boundary is present. The cosmic microwave background, which is the faint residual radiation from the Big Bang, appears almost uniform throughout the celestial sphere. Such consistency would be unattainable if space were to terminate suddenly just beyond our line of sight, thus confirming that the universe stretches further than our observable range. However, its expansion occurs in a manner where a significant portion remains perpetually concealed. What's more disquieting is that this limit isn't static. The visible cosmos expands over time. This is due to light from farther areas having had an extended period to arrive, though simultaneously the universe's expansion is quickening, propelled by dark energy. Currently, space is stretching at a greater velocity than previously. These two phenomena are in opposition. The boundary slowly extends, yet space itself expands at an even quicker pace. Consequently, we inhabit a cosmos where celestial bodies can permanently disappear from sight. Galaxies presently observable will, in due course, pass beyond the cosmic boundary. Their emitted light will extend into progressively longer wavelengths, gradually becoming imperceptible. Ultimately, no fresh photons, originating from those galaxies, will ever arrive at Earth. From our viewpoint, they will seem suspended in time, fixed at a specific point in their past, before gradually diminishing. This isn't mere conjecture, it's a direct outcome of the observed expansion rates. Should dark energy's present behavior persist, then approximately 100 to 150 billion years from now, all galaxies beyond our immediate gravitationally linked cluster will vanish past the visible limit. Future observers will perceive a cosmos comprising just a modest grouping of proximate galaxies enveloped by void. They might never realize that anything else ever came into being. This brings forth a deep insight regarding cosmic viewpoint. The visible universe isn't the entirety of the universe. It's merely the segment of the cosmos that can be observed from our current position at this specific juncture in cosmic history. Relocate to a different galaxy, and the visible universe transforms. New galaxies become apparent, while others recede beyond the boundary. Each point in space establishes its unique observable universe. This gives rise to peculiar scenarios. Two distinct galaxies can both be visible from Earth, but remain incapable of observing one another. They are situated on opposing sides of our horizon. Light from one arrives here, and light from the other also reaches us. However, light from one cannot travel to the other. From their respective viewpoints, Earth itself might be situated beyond their cosmic boundary. No superior vantage point exists. No central or unique position from which the whole cosmos is discernible. The James Webb Space Telescope has heightened our understanding of this constraint by extending observations nearer to the boundary than previously possible. When Webb identifies galaxies with redshifts exceeding 10 or 12, it is observing radiation that commenced its voyage when the cosmos was merely several hundred million years old. These galaxies are presently located far past the origin point of that light. Their present condition, their subsequent development, fusions, and alterations remains beyond our knowledge. That data is still traversing through space, elongated and attenuated. And frequently, it will never reach us. What we perceive is not the present reality. It is what existed in the past, and even that perspective is partial. Beyond the visible boundary resides the unobservable cosmos, areas that could harbor galaxies, clusters, and formations equally as abundant and intricate as the ones we currently observe. Certain theories posit an infinite universe, while others suggest it's finite yet incredibly vast. Regardless, the portion of the universe we can observe is almost certainly just a tiny segment of its entirety. The James Webb Telescope hasn't uncovered the universe's boundary. Instead, it has shown that no accessible edge exists whatsoever. As we face this truth, a further question inevitably arises. Given that cosmic expansion conceals the majority of the universe, what power is causing this acceleration? To address this, we must examine reality's most prevalent and enigmatic component. Initially, when scientists grasped the universe's expansion, the explanation appeared simple. The Big Bang propelled everything outwards, with gravity exerting its influence over eons. Was expected to gradually decelerate that expansion. The cosmos could either continue expanding indefinitely or eventually contract back upon itself. But in either scenario, gravity was anticipated to be the primary power determining its destiny. This presumption was disproven in the late 1990s through observations of remote-type Ia supernovae. These stellar detonations, which emit a consistent luminosity, led astronomers to realize that the universe's expansion was not decelerating. In fact, it was speeding up. Galaxies weren't simply separating due to the Big Bang's residual impetus. Space itself was expanding at an increasing rate over time. This occurred as if propelled by a force opposing gravity across the most immense scales conceivable. To account for this acceleration, researchers coined a new phrase: dark energy. This dark energy is imperceptible to sight or touch, nor can it be directly detected. It neither emits nor absorbs radiation, and does not coalesce into structures like ordinary matter. Its presence is deduced solely from its impact on the universe's expansion, and these impacts are profound. Current measurements now suggest that dark energy constitutes approximately 68% of the cosmos's total energy. Conventional matter, encompassing everything from celestial bodies and galaxies to worlds and individuals, comprises under 5%. Dark matter accounts for the bulk of what's left. The universe we perceive represents a minor fraction of reality. What renders dark energy particularly disquieting is its behavior. As cosmic space expands, regular matter becomes less concentrated. If the volume of space doubles, matter's density halves. Radiation dissipates at an even quicker pace. Dark energy, however, deviates from this trend. Its density stays uniform even while the universe grows. This establishes a self-reinforcing cycle. As space expands, the overall quantity of dark energy rises. An increased amount of dark energy then propels more rapid expansion, which subsequently generates additional space, thereby producing even more dark energy. In the early stages of cosmic history, matter was predominant, and gravity influenced the development of stars and galaxies within the cosmic web. However, as the universe grew and matter became more dispersed, dark energy progressively assumed control approximately 5 billion years ago. Dark energy emerged as the primary factor governing cosmic expansion. While the James Webb Space Telescope doesn't directly observe dark energy, it witnesses its effects universally. The elongation of ancient light, the immense scale of the observable cosmos, and the manner in which remote galaxies separate all demonstrate the impact of this unseen power. Were dark energy absent, the cosmos would be considerably more compact, and the cosmic boundary would be situated significantly nearer to us than its current position. The long-term destiny of the cosmos is also shaped by dark energy. Should its intensity persist unchanged, as contemporary observations indicate, the universe is set to expand indefinitely. As the rate of expansion accelerates over time, galactic clusters will maintain their gravitational cohesion, yet all matter beyond them will ultimately drift past the cosmic event horizon. In trillions of years, inhabitants of our galaxy would perceive a solitary cosmos, comprising solely proximate stars, devoid of any discernible trace of the vaster universe that previously encompassed them. While the universe would persist, it would seem nearly vacant. This scenario, nevertheless, is made intricate by a significant issue within contemporary cosmology. This particular problem, rather than being resolved by James Webb, has instead become more challenging to disregard when researchers quantify the current expansion velocity of the universe. Instead of a singular result, they obtain two. One approach involves examining the early cosmos through the analysis of the cosmic microwave background. This faint residual glow from the Big Bang, emitted when the cosmos was merely 380,000 years old, allows scientists to deduce an expansion velocity of approximately 67 kilometers per second per megaparsec. The alternative technique investigates the proximate universe, where astronomers determine galactic distances utilizing Cepheid variable stars and type Ia supernovae as celestial distance indicators, subsequently contrasting these distances with the recession speed of galaxies. This methodology consistently yields a greater figure, approximately 73 kilometers per second per megaparsec. Both sets of measurements exhibit precision, have undergone numerous repetitions, and have been rigorously checked for systematic inaccuracies. These findings are not in accord. This divergence is termed the Hubble tension, and it constitutes one of the gravest outstanding issues in the field of cosmology. It was anticipated that James Webb would elucidate this matter by furnishing more precise distance determinations. However, Webb instead corroborated the elevated expansion rate observed in the local universe. The discrepancy did not vanish, rather it intensified. This implies a fundamental gap in our comprehension of cosmic expansion. Perhaps dark energy is not constant after all. Its intensity might have varied throughout time. Alternatively, novel physical principles could be influencing the propagation of light across. Immense cosmic expanses, or the primordial universe itself, might have acted in manners that our present theoretical frameworks are unable to account for. Every potential scenario holds significant consequences. The rate of expansion dictates the age, dimensions, and ultimate destiny of the cosmos. Should our understanding be flawed, then numerous inferences, derived from decades of cosmological investigation, might require re-evaluation. Furthermore, a more radical prospect exists that has not yet been dismissed. Should dark energy intensify over time instead of maintaining a steady state, the expansion might ultimately overcome gravitational forces, even at more localized levels. Galactic clusters would be dismembered, galaxies themselves would disintegrate, followed by stellar systems, planets, molecules, and ultimately, in a theoretical event called the Big Rip, atoms might be pulled apart. However, current data does not support this outcome, though some uncertainties persist. Ascertaining the precise nature of dark energy represents a top priority in contemporary astronomy, and the James Webb Space Telescope is pivotal in refining distance measurements. Furthermore, it investigates the early universe, where the expansion's behavior was initially established. What is already apparent is that dark energy holds sway over the cosmos. It governs the universe's expansion, conceals vast portions of reality beyond our grasp, and dictates what future observers will be able to perceive. It is why the observable universe extends across 93 billion light-years, and also why the majority of existence will perpetually remain unseen. Yet dark energy represents only one aspect of the overall narrative. Because while it dictates the universe's expansion, it does not account for how matter organizes itself within that expanding volume. For that, we must consider something equally imperceptible, equally enigmatic, and utterly crucial for cosmic structure. If dark energy dictates how the universe expands, then dark matter governs how the universe maintains its cohesion. Without it, the cosmos unveiled by James Webb would not exist in any discernible form. Galaxies would never have coalesced. Clusters would have dispersed, and the intricate large-scale patterns we observe spanning billions of light-years would have remained an almost uniform haze of matter. Dark matter neither emits light nor absorbs it. It does not interact with electromagnetic radiation in any way that is directly measurable by us. And yet, it outweighs all visible matter by a ratio exceeding 5 to 1. Approximately 85% of all matter in the universe is dark matter, detectable solely through its gravitational influence. The initial indications of its existence surfaced nearly a century ago when astronomers observed that galaxies were exhibiting unusual behavior. Specifically, stars in the outer regions of spiral galaxies were orbiting at an excessively high speed. Based on the visible mass alone, those stars should have been propelled into intergalactic space. Instead, they remained gravitationally bound, moving as if an enormous quantity of unseen mass enveloped the galaxy. That unseen mass was dark matter. As observations improved, the evidence accumulated. Galaxy clusters presented the same issue on larger scales. Individual galaxies were moving too rapidly to be contained, solely by visible matter. Gravitational lensing, the bending of light by massive objects, revealed distortions, considerably stronger than what stars and gas could produce. Repeatedly, the conclusion was inescapable. Most of the universe's matter is invisible. What makes dark matter so crucial is not solely its abundance, but also its behavior. Unlike ordinary matter, dark matter does not collide with itself or dissipate energy through radiation. It traverses space almost without friction. This characteristic allows it to begin clumping very early in cosmic history, shortly after the Big Bang. The cosmos was nearly uniform, exhibiting minute fluctuations in density imprinted during its earliest moments. Dark matter was the first to respond to those fluctuations. Conversely, as conventional matter stayed heated and resisted compression, dark matter initiated the creation of unseen halos, dense accumulations of mass that progressively expanded due to gravitational forces. These halos evolved into the universe's structural framework. With the cosmos cooling, regular matter started gravitating into these dark matter pockets where gas accumulated. It compressed, ultimately sparking the formation of stars. Galaxies did not emerge haphazardly. Instead, they materialized in areas where dark matter had already congregated following an unseen cosmic design. This design, established billions of years prior, resulted in one of the universe's most remarkable characteristics, the cosmic web, observable at the grandest cosmic dimensions. Matter is organized into immense thread-like structures extending tens to hundreds of millions of light years. These filaments converge at compact junctions. These junctions are the sites of galaxy cluster formation. Interspersed among them are vast empty spaces, regions so utterly devoid of galaxies that this arrangement is not a mere aesthetic happenstance. Rather, it is the inherent consequence of gravity exerting influence upon dark matter throughout the universe's history. Observations from the James Webb Space Telescope have clarified this structure with greater precision, unprecedentedly. By documenting hundreds of thousands of galaxies and determining their spatial coordinates and separation, astronomers are able to chart the three-dimensional spatial arrangement of matter throughout the cosmos. The outcome is unequivocal. Galaxies align with filaments, congregating at nodal points. They are absent from empty regions. The observable universe adheres to an unseen framework. What renders the Webb telescope particularly potent is its capacity to penetrate cosmic dust. It can also identify dim, remote galaxies that earlier investigations overlooked. This completes missing sections in the cosmic web, uncovering the early emergence of these formations. The Webb telescope has demonstrated that these filaments were already firmly in place when the universe was just a few billion years into its existence, and that matter was traversing them. This matter was moving towards expanding clusters. This flow is not metaphorical. Both computational models and empirical data indicate that gas flows along dark matter filaments. Much like vehicles on cosmic thoroughfares, galaxies expand not solely through internal star creation, but also by accumulating new matter transported via these unseen pathways. Even our own galaxy is not solitary. The Milky Way is situated upon a filament, linking more massive formations, moving across the cosmos. It travels along trajectories delineated by dark matter. At these scales, movement is not arbitrary. It is directed. Over many decades, dark matter's role within the cosmic web was corroborated, chiefly through simulations and circumstantial proof. Lately, however, astronomers accomplished a significant feat. They directly observed dark matter within the filaments themselves. Employing the phenomenon of gravitational lensing, researchers investigated how light from remote background galaxies was faintly warped as it traversed areas. These areas were theorized to be present with filaments. The warping was subtle, nearly undetectable, yet uniform. It indicated the presence of mass. This mass could not be explained by any observable matter. Dark matter was not merely confined to clusters. It was distributed throughout space, interconnecting the cosmos. This finding converted the cosmic web from a mere theoretical concept into an observable framework. The universe isn't just a scattered assortment of galaxies, drifting aimlessly. Rather, it's an interconnected system, formed and upheld by unseen material. The most massive components of this network are galaxy clusters, gravitationally bound entities known to exist. A solitary cluster might encompass hundreds or thousands of galaxies, alongside extensive reserves of hot gas and immense quantities of dark matter. These clusters serve as gravitational anchors, drawing material along filaments towards their central regions. When galaxies enter clusters, they experience significant transformations. The dense surroundings strip away their gas, cease star formation, and reconfigure their galactic structure. Webb meticulously observed these transformations, capturing galaxies in the process of being reshaped by their environment. The cosmic web is not unchanging. It is dynamic, continuously reallocating matter and energy. Yet, despite its profound influence, dark matter continues to be among the most profound enigmas in physics. Its composition remains unknown. It could be comprised of novel particles beyond the standard model, or involve entirely novel physics. Despite decades of experimental efforts, dark matter has not been directly detected in laboratories, yet still, its existence is undeniable. Each galaxy rotation curve, every gravitational lensing measurement, and every large-scale structure map all indicate the identical conclusion. If dark matter is omitted from the equations, the universe we perceive simply cannot exist. James Webb does not resolve the dark matter enigma. However, it reinforces the argument for its pivotal role by unveiling the early universe in unprecedented detail. Webb demonstrates that structure formed more rapidly and efficiently than visible matter alone would permit. Dark matter supplied the gravitational head start necessary to assemble galaxies so quickly after the Big Bang. It also clarifies the current appearance of the universe, the immense emptiness of cosmic voids, the dense richness of clusters, and the filamentary bridges linking them, all naturally arise when dark matter's gravity is dominant. And yet, even this invisible framework operates within a universe being stretched apart by dark energy. Dark matter constructs structure. Dark energy expands space. The universe exists in a perpetual tension between these two invisible forces. On smaller scales, gravity triumphs. Galaxies form and clusters expand. On larger scales, dark energy predominates, driving galaxies apart and extending regions of space beyond our cosmic horizon. This equilibrium shapes everything we perceive. James Webb has revealed that the universe is not merely larger than anticipated, it is more structured, more interwoven, and relies more heavily on unseen forces than we ever conceived. What we observe, stars, galaxies, nebulae, represents only the illuminated exterior of a far more profound structure, an invisible architecture. Maintaining the coherence of reality, and upon stepping back sufficiently to view this entire framework, a further insight becomes apparent. Even this immense, interwoven cosmos is merely what's perceptible to us from our specific vantage point in time and space, which leads us to the ultimate, inescapable query. Should each observer perceive merely a tiny segment of a far grander reality, what implications does this hold for our position within the cosmos and the very essence of scale itself? The James Webb Space Telescope not only broadened our perspective, it fundamentally altered our perception of our position in existence, unveiling a cosmos that came into being more swiftly, expanded to a greater size, and encompasses significantly more than previously conceived. Trillions of galaxies populate a cosmos influenced by unseen forces, extending over distances beyond our reach. Yet even this entirety, each star, every galaxy, every deep field photograph, constitutes merely what is discernible within our restricted observational aperture. Beyond this point, the cosmos persists, both invisible and inaccessible. Webb's most profound insight is not the volume of our discoveries, but rather the immense amount that will perpetually remain beyond our grasp. The cosmos is immense, not solely in its physical dimensions, but also in its enigmatic depth. And now, for the first time, we can genuinely grasp the inherent narrowness of our perspective. Should you appreciate this video, be sure to hit the like button and subscribe. Your support makes a substantial impact and contributes to the channel's expansion.